All right, so here's how we're going to do notes today because apparently my printer ran out of ink. So you're going to have a computer view of my computer. All right. So either way, today's lesson is 9-4 linear, quadratic, and exponential models. And our objectives are to compare if something is linear, quadratic, or exponential. And then given a set of data, decide which type of function models the data and write that equation to describe the function. So those are our objectives today. Taking a look at our next, center this. All right. Taking a look at our next piece here, we are going to identify something as linear, quadratic, or exponential based on some of this data here. So I'm just going to get back to, there we go. So let's see, training heart rate. We've got an age of 20, 30, 40, 50. And so hopefully you notice that between each of these, you're adding 10. So this is me writing on a computer with a computer mouse. So here we go. All right, so adding 10 as we go between each of these. And so in that case, we do have something that we can then compare the data. All right. Then if we look at the difference between each of these, let's see, 70 to 161.5. If we take 170 and minus 161.5, we've gone down 8.5. All right. And then double checking, if I go from 161.5 to 53, do I subtract? Let's see, 161.5 minus 8.5. We get 153, and then minus 8.5, we get 144.5. So since we have this one common difference, and not to mention, if you look at the graph itself of each of these points, it does make that linear pattern. All right. We can then say that all of this type of data is going to be linear. And remember, linear comes from the word line, right? Linear. All right. So in that case, this is linear. So if we see any of that as we recognize through the notes, we're going to have a linear model. This next one here is our volleyball height. Looks like our time goes from 0.4 to 0.8 to 1 to 1.2. And so it turns out that from here to here is 0.4, but to here is 0.2, and then here to here is 0.2 as well. And so we don't necessarily have a pattern here. And let's see, from here to here to here, let's see, 12, it's 0.76 difference, and then same amount of time, but definitely not 0.7 difference here. This one here, if we connect them, does between linear and exponential make more of a quadratic looking model. So that's actually what this one is going to say. All right. And then the last one is going to be exponential. So as we look here between 1, 2, 3, and 4, definitely has a +1 that's going there. And so because of that, we can say that we have something that we can look for a pattern for over here. Between 16 and 8, we are dividing by 2. Technically, we're subtracting 8, but I can see that we are actually going to be dividing by 2 as we continue. And so in that case, we do have this common ratio. And so because of that, and again, this image that represents what we're looking at, we do have that kind of L-shaped curve that's going down or up very rapidly and then decreasing. So In that case, this is going to be exponential. So the main ideas are linear has a common difference here, and of course it makes a line. Quadratic, if we looked at the table a little bit better, we would in fact see a common second difference. So we'll kind of point that out in a little bit. And then of course the U shape. And then your exponential here has, of course, your common difference in the x's, but in the y's has something that's multiplying or dividing. All right. Looking at our first example here, we're going to graph data and choose a model. So we're going to choose which kind of model best describes this data. So as we look at what's happening, we've got time and bacteria. And so hopefully you've been paying attention in your science classes if you've done any graphs there. The idea is that we are going to pick our scale. Notice that as we're looking at this, we only have 0 to 4, but we have all of these lines to go through. So we may as well skip every other so that we can kind of give it a bigger spread. And that didn't work out because I ended up, let's see if I can get back to my cursor. There it is. I ended up doing 3 boxes between each of those, so that's not helpful. There we go. All right, so we're going to skip every other box. So actually right here, and then here, and here, and here. All right. So over here is going to be our 0. Then we'll have 1, and 2, and 3, and 4. And then over here, we have quite a few lines. I'd say about 20. And we have to go from 24 to 6,144. So, of course, this is going to be an estimate as we are plotting here. There is no way that I have 24 squares and then 6,144 squares. So we're going to make a scale. So again, there are about 20 squares here. And so I need to get to around 6,150, but I can only go up about 20. So all I did was take 6,150-ish or 144 and rounded it, and divided it by 20. And so if we take a look at that, we're getting about 300. So the idea of that then is that each of these increments is going to be about 307. But of course, I'm not going to do that because that seems a little bit too specific. So instead, I'm going to go up by 300s. So this first line, if I was to put a dot right here, would be a coordinate of over 1 up 300. The next one, I'm going to go up to 600. Then I have 900. And then we have, let's see, what is the next one? 1,200. And then 1,500. And then we'd have 1,800, 2,100, 2,400, 2,700, and then 3,000. So I'm going to put that one here at least. All right, then I have 3,300. 3,600, 3,900 would be here, 4,200, 4,500. I may as well mark one of those at least. 4,800 would be this one. 5,100 here. We're getting close. 5,400. 5,700. Oh man, 6,000, and we're kind of off the graph. But I hope we can get the gist of how you would make a scale here. Again, I did not take the time to write each of these in here because I noticed as we're looking through here that basically by the time we get to here, there are no points until we get actually past here. So let's see. If we do a different color for our dots here, the first coordinate that we have is 0, 24. So I'm going to put a dot basically at 0, 0, but a little bit above. Our next coordinate is 196, so that's about a third of the way up. Can't really do that very easily. 2 is 384, and again, we're estimating, so 300 is at the dot, but 84 would be a little bit above that. 3, 1,536, 1,500, but a little bit more. And then the last one would be 4, and then all the way up here somewhere. So hopefully from this image, you can see that we are starting out incrementally slow and then basically growing as fast as possible. And so that one's going to be exponential. So, of course, one other way would be to take the numbers and kind of check out what's happening there. And it turns out that as you go from one to the next, you are actually multiplying by 4. But notice that the problem does actually want you to graph the data. So rather than just looking at the table and noticing that you're multiplying by 4 each time, we did want to double check that we could actually visually see that it was exponential. So that's your exponential idea. All right, then we've got our next one, and we're going to graph each data set and this data set and decide which way is going to be best. So here we go. We are going in our boxes from 1 to 50. So remember that there are definitely not 50 boxes going across here. In fact, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So it looks like there's only 15 boxes, so there's not really a nice way to take 50 and divide it into 15, so we're just going to go by 5s. So right here, I'd start at 0. This one would be 5. Right here would be 10. Then 15, and then 20, and I'm not going to label each one because now that we have 2 digits, it's kind of hard to label each line. And 30, 40. 45, 50. And we're done with the boxes at least. So this would be the boxes axis. The next axis is up here. And so it's reams of paper. All right, paper. That's a terrible looking paper word. Okay. So it looks like we're going to go through these 20 dots until we get to 500. So each of the lines, if we take 500 and divide it by 20, should be about 25 as we go through it. So this first line here is 25. Then we have 50, 75, 100 be here. 125, 150, 175, 200. 225, 250, 275, 300. 325, 350, 375, 400. And then 425, 450, 475, and actually right up here, one box more would be 500. So I guess this is a 19 box side. All right. So if we go ahead and graph each of the coordinates, we're going to go over 1 and up 10. So that's there-ish. Then we're going to go over 5 up 50. So that's going to be in the middle here between 0 and 100. Over 20. So 10, 15, 20 is right here. And then up 200. And then over 50 up 500. And so if you graph this appropriately, as much as it maybe looks like it's growing exponentially, which is actually why this box is the way that it is, we actually have a linear line. So sometimes just looking at the data is not going to help. Sometimes actually graphing it, as much as you see this growth, especially on this side, if we covered this up, you'd say, oh yeah, that's growing exponentially, right? But over here, the boxes themselves or the x values are growing as well. So it ends up being linear. All right. Then this last one here, we're going to talk about which kind of model best describes this data. Notice that we have negative numbers here. So as I put together the scale, I'm going to have negative numbers and then also positive numbers. And then notice that we're going down to negative 14, and then the highest number here is negative 5. So it turns out that I'm going to actually start up here with 0 and go in the middle because we're trying to go to negative 3 and then also positive 3. And so let's see, this will be negative 1, negative 2, negative 3. I don't want to go by squares because I try to make the data look less grouped, and so you don't want it to look too messy. So go ahead and spread out to every other dot for your x values. So 1, 2, and 3. And then our y values are going to go all the way down to 14. And since I just said in the last one that this is a 19 box grid, we can go ahead and actually just go by ones. So 3, 4, negative 5 would be here. We have negative 6, negative 7, negative 8, negative 9, negative 10 here. Negative 11, negative 12, negative 13, negative 14, and negative 15. All right. So going ahead and graphing this, we're going to go over negative 3 down negative 14. So we're going to put a dot here. And of course, we are going to be doing a quadratic, even though we don't necessarily know at this point, but based on most of my notes and the system here, we've already done an exponential and a linear, so the only other option is your quadratic. All right, so then negative 2, negative 9 is going to be here. Negative 1, negative 6 is over here. So it's kind of looking linear, but then if we go from 0, negative 5, oh, my plotted point's a little off. And then 1, negative 6, 2, negative 9, and 3, negative 14. We do end up having this upside down U shape or quadratic parabola here. Again, drawing with a mouse, so we're just gonna go with what we get. All right. So that one is quadratic. Again, hopefully you can see that shape making sense. Oh, apparently I just deleted my axes. Okay. Just put those back in. All right. So next one here, when the independent variable changes by a constant amount, the functions linear functions have constant first differences. So this is when we're talking about tables. I got it. Okay. So again, this is when we're looking at a table and not just a graph. All right. If we're looking at quadratic equations, which is one power up from linear, they have a constant second difference. So that means that you're going to take each of these first differences and subtract them, and that would be your second difference. All right, and then the last piece here is your exponential. And your exponential functions have a constant, what we call ratio. And so that constant ratio means that there is something that is divided or multiplied instead of added or subtracted, which would be your first difference or your second difference. All right. So taking a look at our table, again, we're trying to use patterns to choose a model. So if the independent variable, which is the x value, so I'll indicate that, is constant, and taking a look at these x values, 0, 1, 2, 3, 4, those are constant. All we need to do is double check how we get from 4 to 68 to 100 to 100 to 68. So I don't necessarily see a number that would multiply by 4 to get 68, but let's check. Apparently it's 17. And so then if I take 68 and multiply by 17, I get 1,156. So this is not multiplying by 17 as much as we see that. So then we're going to start adding and subtracting. So 4 plus 64 is going to get 68. 68 plus, 32 makes a 100. We have 100 to 100, which would be plus nothing. And then from 100 to 68 subtracts 32. So that's what we call our first differences. And so notice that our first differences are not the same. And so we can then determine that it is not linear. Again, we already determined it's not exponential because there's nothing that multiplies. So we're going to say that as well, exponential. Wow, I can type so well and write. Okay. All right. So then we're going to move on to our second differences. So all I need to do is decipher between the 64 and the 32. And so I'm looking at 64 and 32 and saying, well, between those two, I would go down 32. Between 32 and 0, I need to subtract 32. And between 0 to negative 32, I subtract 32 as well. And so notice that those are our second differences. And that means that we now have something that is quadratic because they are all the same. If one of them was like a 33 or something, we would not be able to say a quadratic. We'd say nothing. All right. So then we move on to the next one here. And again, probably because of the way notes are used, this is not going to be quadratic. So we're going to find our difference between 100 and 1,169. So the two differences could either be that we're adding $169.86, or the other option could be that we are multiplying. So what is 1,169.86 divided by 1,000. So we could also be multiplying by 1.16986. Wow, that's a great number. All right, so then we just need to check what's happening from one to the next. So am I going to take 1,169.86 and add 169.86? Oops. Apparently I'm running low on battery. And it turns out that I would hopefully end up with 1,339.72, which is not the next number. So it turns out adding is not what we're doing. Instead, we're going to multiply by this kind of terrible digit. So 1,169.86 times 1.1686 brings us to 1,367.09. Oh, well, that's because I missed a digit, 986. There we go. Now it's exact. 1,368.57, which apparently is off by 10 cents. Anyway, so turns out we are multiplying by 1.16986. And then also to the next one. And so because we have what we call a constant ratio, we now know that this is exponential. Man, I look like I'm writing with my wrong hand or something. Exponential. All right. So moving on to the next one as I plug in my computer. All right. We're looking for a pattern in this data set. So taking a look at what we have here. We do have a constant difference between our data over on the left. And then if we look at the difference between the data here, between 10 and 1, we're going to add 9. Between 1 and negative 2, we're subtracting 3. Between negative 1 and negative 2 and 3, we're adding 3. And then between 1 and 10, we have adding 9. Oh, and by adding 9 in this one, I mean subtracting 9. Okay, so that's our first difference again. And so our first difference doesn't work, and so in that case, it's not linear. So then we move on and try our second difference. And so between negative 9 and 3, to get from negative 9 to 3, you'd add 6. From negative 3 to positive 3, you'd add 6. And from positive 3 to 9, you'd add 6. And so now, because our second difference is the same, we now have a quadratic equation. Again, if you went ahead and plotted, you would have noticed that these are quadratic, all right? But turns out that we can see it through the data as well. All right, so the next piece here is deciding which model best fits the data and writing a function. So for instance, now that we knew this was quadratic, what would be the equation that we would use in order to get from one data point to the next? So first thing is the linear equation. So notice that we have y equals mx plus b. Your m is actually what we're going to call our first difference. So once you find out what your first difference is, that number that's added or subtracted a bunch of times, we can go ahead and plug that in. The next piece, looking at our data, is the b value. And the b value is actually going to come when the coordinate is 0 and then has a number. So whatever that number happens to be, we can plug in for the b. All right, quadratics are actually not as easy to identify. And so for a quadratic equation, the only thing that we can really actually see is this value here, which is going to be its intercept, actually. So 0, c gives us where the intercept is. Otherwise, the other pieces that we have to find are not as easily identifiable, and so we won't be actually writing quadratic models. The next one here is your exponential. And so this a value here is going to represent what your intercept is. So again, each one of these has kind of an idea of where the intercept is. And then the next piece, your b value, is going to be your constant ratio, which we have identified a bit. So b is your constant ratio. So what is it that you are multiplying or adding a bunch of times? All right. So looking at our first example here, we're going to write a function of this data. And we're going to use it to predict the amount of water in the pool after 3 hours. So we'll have a time here in minutes of 3 hours. So we're actually kind of extending this table and saying what would happen in 3 hours. And 3 hours in minutes is 60 3 times. So 180. All right, so we'll get to that once we get our model. So taking a look at what we have here, we have a 10, a 20, 30, 40, and so it does go up by a constant rate here. So now we can identify what's happening here. So between 327 and 342, we're adding 30, 15. If we double check, 342 plus 15 will make 357. And then 357 plus 15 makes 372. And so we know that our first difference is 15. And so because of that, we know that it's linear.
His truck is here.
Okay.
And his truck is here.
Okay, thank you. Can you guys go because I'm recording a video?
What?
I'm recording a video, sillies. All right. So we're going to write the equation, and remember that the equation is going to be mx plus b. All right. Where m is this 15 that we just identified, and b has to be at 0. So another way of finding out what's going to happen at 0 is kind of extending this pattern. So notice that if we go down to 0 in our table, instead of adding 15, we'd subtract 15. So 327 minus 15 leaves you with 312. And so we know that our b value is 312, and so our equation can be y equals 15x plus 312. All right, then we can use this equation to find out what happens after 3 hours. Most likely when they're saying 3 hours, you're thinking that you'd plug in a 3, but it turns out that we're plugging in a 180. So into this x right here, we're going to plug in 180. Take that 180 and multiply it by 15. And once we multiply that number by 15, because of the order of operations, we would add 312. So 15 times 180 is 2,700 plus 312 makes 3,012. So there are going to be 3,012 gallons left, of water in the pool as we're filling it up. Yikes. Okay. So it turns out if you're filling up a pool, your growth is going to be linear. All right. So apparently that is our last example 7 there. And so hopefully we now have a better understanding of how to identify an equation. Again, we're comparing linear, quadratic, and exponential models. And that main idea is that in a linear equation, you have a line, of course, that you're drawing, but also that there's this constant first difference. In a quadratic, you end up having this parabola shape, and then you have a constant second difference once you subtract. And then in your exponential, you have a constant ratio versus a addition or subtraction. So in this case, dividing by 2.